And now let's continue and let's see, this is last lecture, let's see how we can have a broader view involving causality and other problems. So essentially, intuitively, we know causality is really a fundamental notion. We ask why, right, all the time. Then you are going to see that in many cases, yes, indeed, caring about why is meaningful, right? It's actually even necessary. Let me finish the previous one right here. I'll go through this part very quickly. Some of them will be repeated later. So now, in the morning, you saw how we could just discover latent variables and the whole picture in the ID case with a single distribution, right? And now let's go from there. Suppose we have multiple distributions. What can we do? Yesterday, actually, you learned something about it. Causal discovery from non-stationary data, CD node. Basically, you can still discover causality, and you can, oh no, in the morning you saw it at the very beginning. So we can even benefit from the property that modules change independently, right? If you have non-stationarity. That's good. Now we focus more on the latent variables. And then let's see how we can proceed. First of all, as Ija just said, in a general nonlinear case, forget about kind of causality with latent variables. Even nonlinear ICA does not have a meaningful solution. In a linear case, we can really discover everything, including latent variables to some extent, and the causal direction among the measured variables, because we have the identifiability of ICA. And even with overcomputed ICA, we have some kind of identifiability. We can estimate the mixing procedure up to something kind of some equivalent class. Essentially, we can still estimate all those columns up to some permutation and rescaling factors. That's good. In the nonlinear case, unfortunately, as you can see from Vijaya's presentation, it's not possible. That's why he introduced specific type of sparsity. And that's why we say it's the beginning of the work. Why? Because in that work, you assume the latent variable is independent, and that's the generate what you observe. You don't allow causal relation among the measured variables and so on, right? In another piece of work by Lin Jin, my student, you can just basically deal with nonlinearity in a different way. But in any case, right now, in the general nonlinear situation, under the IID assumption, it's really hard to recover the underlying truth. But if you have non-stationary data on multiple distributions, all of a sudden, you can go beyond, you can go much further. As you can see from here, so if you assume this is a recent advance in nonlinear ICA by Apple and others, then you can easily see why that's the case. So Zi are independent variables. They're independent, right? And suppose you have multiple domains. Say you care about females, males, and the kids, right? And they have different different groups, and they have different distributions. Suppose that in each group or each domain, the underlying variables are always independent. In other words, you may say they are conditionally independent given the domain, right? In each domain, they are independent. Then if you have enough domains, and if you assume that the mixing procedure in ICA, which is here, this G function, this is the mapping from the underlying independent variable to the mixing, to the observed variables, right? This guy is fixed. Then you can estimate each of those independent sources up to a trivial component-wise invertible transformation. That means you can recover each of them without much difficulty. Why? Why can you do so? You can easily establish the intuition right here. You observe a lot of domains, right? First domain, second domain, third domain, and so on. How can we solve say system linear equations? We have multiple equations, and then finally the number of unknowns is smaller than or equal to the total number of constraints, right? This is how we have enough information to determine the underlying unknowns. Now, suppose across all those domains, the measured information is invariant, is shared across domains, which is the function G. G is invariant. You only allow changes in the distribution of the independent variables. Distribution of Z1 or Z2, right, could change across domains, but they are always condition independent. Now you can see if you go from one domain to another, the change or the amount of information you have to change is very minimal. It's just a marginal distribution of the separate independent sources, right? And in this way, as you have more and more domains, each domain contains a lot of new information. You can see since the G function G right here is shared, eventually, as long as the number of the degree of freedom, right, introduced by the changing distribution of the marginal distribution is not very high, you can benefit from more and more domains. And as a consequence, you can just determine everything, right? You can determine the function G. This is nothing but another instantiation of minimal changes. So yes, you allow changes. However, the changes are minimal. In this case, they only happen to the marginal distributions of the independent variables. And then since you have more and more domains, you have the information to determine the invariant part, which is the function G. As long as you have G, you have everything, because you can recover the underlying variables by considering the inverse of the mapping G.
G is constant, and also the invariance mechanism. We also assume both, like y given x is a
wonderful. Yes. Here you assume G is invariant. Let me give one example to at least to show that it's reasonable in some cases. Suppose the underlying variables Zi are underlying concepts. You try to produce a picture, right? The picture basically is a function of the underlying concepts, right? Like what you have and the property of the things you have in the picture and so on. So Zi's are latent variables right there. However, once you have the concepts, if you specify the concepts of these, then the generating process from them to the picture would be the same, right? Suppose you are using the same camera, for instance. Good. So in many cases, yes, you can assume that the generating process from the underlying independent factors to the measured variables is fixed. Good. Now you can see why you can have the identifiability. It's just a minimal change. I can make sure that each time when I have more domains, I can have more information. I can gain some more information about the invariant part, which is the function, the mapping G. That's it. Okay. And this is basically the idea of the proof. Now let's go further. So this is also a recent paper by Linjing Shaoan and Yu Jia and others right here. In many cases, not all those underlying factors change, right? Think of images in different domains, right? If you take images at different in the morning, in the noon, and then in the afternoon, you can see they still share a lot of information, right? You cannot assume that all the underlying independent factors change. So here, you just allow a small number of factors, underlying factors, to change. Okay, and then now we show the following thing. This part, all those changing components are completely identifiable up to some kind of component-wise transformation. Furthermore, the invariant part can be recovered up to the some kind of subspace. Okay, this is very good. Why? Because if you have this way to look at the differences, you can really understand the essential difference. How can we learn the concepts? How can we really learn things across different scenarios? How? I think you clearly thought about the problem. The class is grade 1, we learn something, and then grade 2 we learn something changes, right? And then we are going to focus on the changing part, and so on. So when you try to understand the different things, you try to introduce a minimal change, minimal difference to align different domains. Now I say, compared to grade 1, this part is different, right? So this is exactly what this method is doing. You have multiple domains. You want to introduce a minimal number of changes to align the domains so that you can really see the connection among all those domains. This is how we understand the different things and how we can learn things by contrast, right? Okay, and there's another thing which is interesting. Usually, if you don't have the minimal change constraint, then the change part can be meaningless. Why? Because suppose I have Z1 right here, this one changes, and Z2 right here. Suppose this guy does not change, then any combination of them will change, essentially, right? So if you put invariant things into the changing part, then they change, right? So that means without the further constraint, we cannot really discover the meaningful changing part to explain the difference. This is what I mean by minimal change. You'll see that in 1 minute. Another advantage of this framework is as follows. Suppose I want to do domain adaptation. I have multiple domains. I have pictures taken in the morning, in the noon, in the afternoon. I would like to do domain adaptation in the morning and in the noon. I have labels. In the afternoon, I don't have that. Now I try to do the information transfer. What can we do? With this framework, you know, all those things, invariant part is shared. It's the same thing. Only this part is different. Then you just try to align the changing part. After that, you can really see the correspondence across different domains. In other words, if you are given something in the morning, you know the counterpart in the noon and at noon, and then you know the counterpart in the afternoon. Okay, you will see how we can apply this. So for domain adaptation or transfer learning, you can see with this framework, generally speaking, the performance accuracy is very good. Why? Because you can really see the correspondence information across domains. Then you can do transfer. And right here, I just explained this problem. You saw this picture before. We have photos, images from the summer and images from the winter. Right here, they're not paired. We just have arbitrary set of images, right? And then you are given, there are multiple tasks involving this setting. For instance, in one case, you are given, say, different from this example, you are given your picture. You want to produce some kind of anime, right? You have selfie, and then you want to produce the corresponding anime. What can we do? You just collect the two sets of images. They are not necessarily paired, right? You want to do translation. You want to change images, right? Selfie to anime, for instance, or you want to transform the summer image of this particular scene to a counterpart in the winter. How can you solve the problem? And another related problem is data generation. I just want to generate data, say, corresponding to different seasons. I want to make sure they have the same content. It's similar because you have to preserve something, which is the content. So here you can see the picture. It's causality because image contains two parts. Content and style, right, is a consequence or is a function of the content and style. And here you want to preserve the information of content and you want to change style. That's it. The problem is, this is kind of very intuitive. The problem is, how can you distinguish between content and style? How can you determine style, right? As I explained in the first lecture, this example might be too complex. Remember this one. Actually, you just showed this one. MNIST data. You have data set. You have the first data set. You have a lot of images here, 0, 1, 2, 2, and so on. A lot of images. And then you are giving another one. Oh, this one is not good. Doesn't matter. Here you have levels, right? Suppose you already know it. Now, how can you do classification? Or how can you allow the machine to recognize those digits? Clearly, the distribution is different across the domains, right? Now you can say, clearly you say, oh, this is just one. There's just a very simple change, very simple operation right here. This is 1, this is 0, this is 1. And I see the correspondence information because I can see what I mean by style. Here, what's the style?
Shape.
Shape or, yeah, more specifically angle, right? Very good, yeah. Basically the shape or angle. Right here, we know that But for machines, as I just mentioned, if you put something invariant as part of the changing part, it's still valid. For instance, I can just say, suppose this is the first day I have been here. I'm from another planet. Then I say, oh, in that world, 0 actually will correspond to 1 after you do something. 1 corresponds to 0, and so on. It's still mapping, right? I can do so. In principle, this problem is ill-posed. All those problems involving domain adaptation, image translation, right, are basically ill-posed. Why? Because you are trying to go from the separate domains to the joint information. In other words, there's a kind of classical problem. You have marginal distributions, and you want to establish the joint distribution. That's almost impossible. You have to make assumptions, right? For us, we can see if we see this, we can immediately identify how they are related, because we just try to use a minimal change to explain the difference, right? I will not go this way, because yes, I see there's something redundant, right? I don't have to go that far, to really explain what I see here. It's just angle. It's very simple. How can you just find a way so that the machines can follow you? That's why this one is related to the previous framework. So you just try to, right here, you try to use as few changing components as possible to match or to understand all domains. I can reproduce the distribution across domains. At the same time, I just use a very small number of changing components. For instance, suppose you have pictures, right? In the morning and noon in the afternoon, then you will just learn the illumination condition, right? You can learn it. It's a kind of probably it's a single factor, although the transformation can be very complex. In this case, it's similar. You may have snow right here and there, right there. If you kind of have, you see something like a tree is going to be green right here. The tree is going to be either yellow or white, right? So you can learn such a thing from data by matching the distributions across domains, and furthermore, by enforcing a minimal change principle. Okay, this is the idea. Oh, this, wonderful. Yeah, you'll see that. Yes. So this is given, that's for the previous one for domain adaptation. This one is given in this paper. So you can see multi-domain image generation and translation with identifiability guarantees. And here specifically is the image. For image data, generally speaking, we have to use very good generative models. That's why generative AI is so popular, right? Otherwise, the images are not really if the quality is very low, right? You will not say it's a very good way to demonstrate what you can do. So here in this framework, we use the GAN, generative adversarial networks to generate images. And here you can see some samples, right? And you can, the idea is very clear. It's also causal way to look at the process. I assume that the images right here, I have a training data set right here. You can see a lot of images, right? MNIST data. I assume that there's a way to generate the images or distribution to produce the distribution of the data by applying a transformation or generator to some noise. You can always generate noise, white noise, right? As you can see from here. And then you can apply some generator, just mapping. And then you try to make sure that after this mapping, this output and the data set have the same distribution. So in some way, I just want to find a generative way to produce the distribution you have in the training data, right? This is just again. And of course, here you have discriminator. It's nothing but a system trying to distinguish between the fake image you generated by the system and the real images, right? And finally, you want to distribute. You like the distribution to be identical across the true training data and the generated data. If you manage to do so, then basically you produce a distribution of the data, right? This is again, that's it. And right here you can see this is the cost function. It's exactly what I just explained. I will skip the equation. Now, if you have multiple domains, you can use the gain to really do the alignment. So here we have a lot of noise. They have the same distribution across domains. U is the domain index. Domain index. So here, this part is invariant, the same distribution. I have one way to produce different distributions for some of the input noise variables. Okay, I can use, say, in the first domain, I have a standard normal. In the second one, I apply transformation to standard normal. I have another distribution. In the third one, I'll apply another transformation to standard normal. I produce another distribution, right? And then with the same generator, remember this is always shared right now. At some point this year, probably it's not a good idea. Next year, we will be able to produce something where G can change. You can see how you can handle that problem. And then with this, you want to model the distribution for each domain. If U is 1, you can produce a distribution in the first domain. If U is 2, you can produce a distribution in the second domain, right? So essentially, this is the same as the previous picture where you have the Z, S, the C. This part can change across domains. And then with the fixed function G, you produce X, the distribution of X in each domain. Now, coming to the problem, we have to make sure that the changing part is as minimal as possible. How can we do it? Essentially, we use some penalty to prefer invariant distribution across domains. So essentially, one thing, I will not talk about technical detail, but basically it's very simple. And then by controlling this parameter lambda, we can control how many components you want to keep as a constant ones. Okay, so if lambda is larger, then there will be fewer components with changing distributions. If lambda is 0, then everything can change, because when we here in the illustration, I have epsilon s for style, epsilon c for content. But in the implementation, we don't have that. We allow everything to change. But with the penalty, we just try to push as many of them to the constant, to the same thing. That's the implementation. Okay, good. Now let's see some result. The idea is to match the distributions in all those domains, separate domains, with the minimal number of changing components. And if you manage to do so, then we can see the correspondence information across domains. So correspondence information is identifiable. Given this image right here in the first domain, I can see the counterpart in the second domain. This is what I mean by identifiable correspondence information. And right here, we have two separate sets of images corresponding to the females and males. Clearly, we don't have pairing information, right? We don't have a person who is a female and a male at the same time, right? So that's why we don't have pair information. We just have unpaired data. Now let's see what we can learn. This is for data generation. I want to generate data, and I want to guarantee that they share the same content but different style. Since now we have two separate images with different genders, they will have the difference. Will explain what you mean by the difference in gender, right? Hopefully that's the case. Now you can see the result by different methods. This is by our method with identifiability guarantees, and this kind of you can also see the results produced by other set of other methods. This is style gain, and this is tensor gain right here. Which one do you think is the best? Yes, ours. I like it. Yes, you preserve as much information possible, right? And just really change the gender. Wonderful. We are so sharp. Okay, and here you can see a lot of new results. Basically, if lambda is 0, as I just mentioned, then you don't have penalty. Anything can change, right? You don't have minimal change thing. You can see it's not so good. Here, still, we'll try to produce images. Sometimes it's good, sometimes it's not very good. For the first one, right? You see glasses. This is extra thing. It shouldn't happen. And on the right, you can see it's always good. Right? The underlying content seems to be the same. If we have a way to change only gender, then it should go this way, right? Okay, And you can see a lot of very small. You may have a look later. So basically it's the same thing. You can just tiger, dog, and cat. Still, although they are different animals, we can still see the shared information very clearly. Okay, including say the gesture and so on. Okay. So if you yeah.
I'm not familiar with data generation that much, but tell me, like, how do you preserve like
diversity of
yeah, like
oh I see. So you want to I see. Basically, you preserve diversity. You can preserve diversity because of two things. First, in this framework, you can see you try to preserve the distribution in each domain. If something happens in the domain, you should preserve such information. There's a chance for you to generate something similar. Second of all, we have noise as input. Then with different kind of noise values, you can produce a different thing. Eventually, asymptotically speaking, if you have enough, if you really have the distribution for the noise, if you know it, then you know I preserve that whole diversity in the data. Of course, I cannot go beyond the data. That's a problem. Later you can see, in the first lecture, I showed some pictures generated by Stable Diffusion. Unfortunately, right now, with this method, we may be able to go beyond the data in some way, but we haven't done that. But basically, in all those tools for generative AI, we can pretty safely say that you cannot reliably go beyond the data because you don't know the concepts. Machines don't know the concept. Machines don't know how to operate, how to combine, or how to check them to produce something meaningful, right? So in the long run, you really have to find a way so that machines can really learn those concepts we care about, and they can really figure out how to put them together, right? And what to change in order to produce a new scenario which is sensible. For now, it's not possible because they are not at that level. They don't have the latent variables at that level. Does that answer the question? Okay. Any other question?
So that is point.
Zero and style, I mean?
I mean
In the style.
Normal zero. And well, person one's style and person two's styles changes. So both of them can write zero, but they have differences. I assume that
Yes.
they actually have each style, assuming each person's style is actually constant.
Wonderful. Not constant, not style. Oh, okay. Now there are two things. I see the point. There are two things actually which are related. One, you assume the style here is the same. This is the first question. Second, you can go further. Probably in the second data set, you don't have such a thing. How can you do the matching? Right? Wonderful. Actually, we can have a relatively straightforward way to solve both problems. First of all, here you may have a mixture. Then I can just use multiple gains, multiple things right here. I can allow a mixture right here to match the single domain. Right? This is a multimodal gain. You can match, you can solve the first problem. You allow multiple values of a style in the same domain. This is one thing. Okay. Second, you may not really have the same content or the same distribution of the content. In this case, also Sean, my student, did something. There are multiple ways to solve the problem. One way is to do the following thing. I know that, but I know that if I remove this guy in this domain, the mapping will still be simple. You can use important rewriting on the data points to remove those unnecessary or unaligned data points. Then you can still align them. And then you can go further. Without a way, a precise or quantitative way to measure how natural or how simple the change is, then this method may fail. Why? Because you remove this one because after that, the mapping is simple, right? If you don't have a very good way to measure how simple it is, how can you really make sure the method is doing the right thing? Now, if we can put them together, one is to have an important reweighting coefficient for the data. The other is to leverage the minimal change thing as a quantitative measure of the complexity of the mapping, right? Because if you remove this guy instead, then when suppose 0 is mapped to 1, you have to suffer more changing components. It's more complex. Putting them together, you have a beautiful framework to solve the problem. Right here, I'm talking about basic thing. There are many variants, right, to deal with all those problems. Good. Okay, cool. Any other questions? Let's go further. Finally, let's make use of temporal information. I will give some very quick example. First of all, in granular causality, we know we make use of temporal information. Then the direction is implied by temporal information, right? It's good. We know effects cannot happen before the causes. It's good. We always benefit from temporal information. And in this case, in this work, basically, we do the following thing. Oh, you saw this picture. No, we didn't see the detail. So right here, we have high dimensional images right here. We have high dimensional images on the left. High dimensional video data as a high dimensional time series. In video understanding, you try to see the underlying things, meaningful things, right, from the video. And then you can assume that, like the image case, you can assume that the video is nothing but a function, unknown invertible function of the underlying latent, meaningful latent processes. Right? For the latent process, they can influence each other. One object can change another object and so on. Right? So in other words, X high dimensional factor here, X right here is the function of the underlying process Z. Z is the underlying latent process, and the different components of Z can be causally related. So suppose we are two latent processes, you can influence me after some steps, I can influence you after some steps. In reality, if you have time series, usually it takes some time for causal influence to take place. So for them, for the two processes, it takes some time for causal influence to take place. As a consequence, for this guy, equivalently, we assume that for the latent processes, we are conditionally independent given the past. Because yesterday, right, your value that happened yesterday may influence my current value. And similarly, my current value may influence your value in 2 days, right? So that means we don't have instantaneous causal relationship. It's time delayed. Then given the past, given the common causes, we are conditionally independent. This is the only assumption, the only one. Then the function G can be non-parametric. The causal relation is right here for the Z, for how we influence each other can be non-parametric. Everything can be non-parametric, but you can show that under this assumption, Zi are conditionally independent given the past. The components ZT can be recovered up to the component-wise transformation. You can recover them. Usually, we don't care about the component-wise transformation because it's the same thing. You just have an additional distortion, right? We don't care because it does not change anything about the independence or dependence. Good, so that's the idea. Conditional independence or this kind of lack of instantaneous relationship is so important. And it makes sense. Why? Because it takes time for causal influences to take place. Here you can see some result, and then I will say a few more words about it.
Cities are independent.
These are independent given the past.
No, but within each other, because it seems that each one is like conditionally independent given its own past, the past of others.
No, okay, I see the point. Let me just draw something right here. We have Z1, Z2. Let me give an example. We have Z1, T minus 1, Z1, T, Z1 T plus 1, right? And similarly, you have Z2, 1, 2, T minus 1. So you here clearly you can allow such relations. You can also allow such relations, right? It's completely flexible as long as you don't have this. This is the problem. If you really want to, if you really have a problem where you have such links, you have to wait probably 1 year, then you can see a solution. But for now, there's no solution, no good solution. Okay, there's no such link. That's the assumption. Good. So right here, you can see a kind of comparison of different methods. The first one is, I forgot it, PCL contractive learning. P is for, I forgot it, but basically it was proposed by apportion learning. And the second one is generalized contractive learning and so on. So you can see with this framework, essentially you can allow time-varying relations, you allow causally related latent processes, you allow kind of partitioned subspaces. So even if you have this kind of link, this is a subspace, you can separate this subspace from the remaining information, although you cannot determine each of them. Okay, is subspace. And you can have non-parametric transition, and you can also deal with non-stationary environments where I don't have any change in the distribution. Okay, good. In all those cases, you have identifiability. And, oh, it doesn't work. That's why each time. Okay, forget it. I use iPad. So the to save time, I talked about this before. Did I talk about this example in the first lecture? Yeah. Okay, good. Now we can make it quick. So we have video right here. Video with the data sets, with the 5 balls. Yeah, right there. And then just with the video as input, right? Each frame is a time instance, and then each pixel is a variable. You have that as input. You can produce, the method will estimate 10 latent processes. They turn out to be the X and Y coordinates of the balls. So basically, then learn, the method can learn to focus on just the balls. At the same time, they can really recover the relations, because between some of the balls, there's a hidden spring. Now you can really recover where the springs are and how they are related to each other. Okay, from video data. Good. So you can really go beyond what you observe to recover the underlying processes. In addition, even if you just care about prediction, you can see this method makes perfect sense. Why? If you go to the right representation, then there are no instantaneous dependence. All the dependence is time delayed. What does it mean? It means that all the dependence information can be used for prediction. If you have instantaneous dependence, it's a waste of dependence because you cannot use it for prediction, right? So if you want to make prediction, you still want to go to this world, make prediction, and then if you want to predict X, you can just go back, right, to construct the value of X. But this is one way for you to really make sure all the dependence information is time delayed so that you can make use of it to make prediction. And this is also how we want to learn the underlying concepts. We try to maximize some kind of predictability because we try to make sure it's under control and we want to make good predictability, right, intuitively. So we also follow this principle. You want to maximize the predictability so that you can really find the meaningful representations, right? Okay. This is the.
Can it be used for compression?
Sorry?
Can it be used for video compression?
I would say yes, because this way you can really separate, you can understand the machine, can understand what's going on, and then can just preserve the measure information. Yeah. Okay, so to summarize, you can have a look at right here, the current results in this space, and on the very right, you can see what we can get at this moment, right? Clearly, as I said before, this field is very quickly evolving. So maybe next year, or in 2 years, your result will be somewhere here. Okay, so summarize, it's essential to learn causal variables in many cases. Today we just talk about fundamental ones. There are so many variants, right? So many modifications to solve real problems. And you can see it's even possible to do it in the IID case. And generally speaking, we benefit from distribution shift and temporal information. And in the future, maybe you want to develop even more efficient frameworks in both the IID case and the non-IID case. And you want to show the necessary and sufficient condition under which you can really recover the truth. Right now, only in some situations, do we have some necessary and sufficient condition? For instance, if it's linear and Gaussian, then we have necessary and sufficient condition on the graph so that it is identifiable. In the linear Gaussian case, some people are working on it, so you can also see it. And in the nonlinear case, basically, this is the open problem. And what if you have changing relations among the hidden variables? You criticize that setting. G is assumed to be invariant, but in some other settings, in some other problems, G may not be fixed, right? So you can even have, here we assume latent variables, generally speaking, latent variables are independent. If the latent variables are causally related, and if the causal influences change, then you cannot produce independent components. You can easily show that, okay? So if that's the case, how can you still learn the meaningful latent variables? Okay, let me make sure you really see what I mean. Suppose you have latent variables Z1 and Z2 right here. This is in the hidden world, right? They generate what you observe. Suppose this guy changes. Then you cannot use the independent components to produce what you observe. In this case, what can you do? And this is very interesting because very oftentimes we learn concepts because of this kind of changes, right? So there's some progress right here within the group. Hopefully within 1 year, you can see new way to look at, to really relax the setting to recover the underlying hidden variables. Okay, any questions? Good. Now let's go further. Can you send a message to Zeri? Yeah. Ask him to give presentation in. Probably let's ask him to stand by. Thank you. Okay. Now let's try to have a look at a number of research machine learning problems from a causal perspective. Here you can see a list. I will just give some examples. Let's have a look at the semi-circular learning, right? You can see why, in fact, with the causality, you may even foresee the result of the method before you apply the method, thanks to the causal understanding of the problem. You see how we can view domain adaptation or transfer learning from the causal perspective. You can see how we can do translation. Actually, I already explained this part, so right here I will skip this part. And the last part is about fairness in machine learning. You can see how the fairness notion or multiple notions of fairness are related to causality and how we can really achieve process fairness in the long run if you really care about the process. Fairness is basically about the process. It's not just observational, right? Because we care about the influences. Okay. Now it works. So here, let's look at the problem of clustering right here. Okay, so in clustering is very simple. You put things together, right? Without making use of the value of y, because I don't have y. Why do you think it's possible? As I explained right here, in clustering, here let x be the features, say different features of the y, right? And you want to say something about the y, which is unknown. If x called y, we know it's not possible. right? Because Px does not contain any information about Py given x. When you try to see the information y, you just make use of the conditional distribution of y given x. Right? Given this x value, I know y should be that value. Right? So if x equals y without latent compounder, it's not possible. If y equals x, then generally speaking, it's possible. That's why we can do clustering to recover the information of, say, gender. Right? Gender causes height, weight, and so on. Then you can really do clustering to recover the underlying core information of the underlying cause. There are so many problems, so many examples. For instance, if you do clustering on MNIST data where you have handwritten digits, it's very easy for you to group ones together, twos together, and so on. Why? Because basically you are recovering the label information. The label is the cause of the digit you actually have, right? So that's why you can always do clustering to derive the information that is hidden, but causal to the measured variables. Here you can see semi-super learning. Basically, suppose we have only two labeled data points for which you have not only x but also y values, right? This is a positive class, negative class. In addition to that, we also have a lot of unlabeled data. Very often times we have such a setting because we can easily collect a lot of data without labels. You observe so many things, right? Now the question is whether you can benefit from all those unlabeled data when you try to find a better kind of classifier or regression model. In this example, do you think you can do so? Right here, if you are given only the two labeled data points, then the decision boundary can be here, or here, or here, here, right? Anywhere. But now, given those new data points, would you like to go here? No, right? And probably you want to go there, this way. Why? When you do this, you can see you actually pay attention to the distribution of x. Is that right? Meaning that you want to make use of the dependence between some kind of dependence between Px oh no, I should learn to use the iPad. So right here, you can see clearly you want to make use of the dependence between Px, some kind of dependence, not a statistical dependence, Py given x. That's exactly what you did here. You make use of the x distribution and say, I don't want to go through the region where the density of x is very high, right? Okay, so if x or y is not possible, if y equals x is possible, if that compounder is possible. Now let's see evidence. Here you can see the typical setting in semi-super learning. You can just give a causal interpretation. I will skip this part because it's technical. Right here, we divide the data sets into causal data sets and anti-causal data sets or compounded data sets. So right here. So this result was reported by some other people, right? They developed very good methods and then they analyze all the data sets. And here let's just do a meta-analysis. Let's see whether we can really understand what's going on. So right here, the blue one is error, root mean square error, produced by the simplified learning method, which ignores the unlabeled data. And the red one is produced by semi-super learning based method. Specifically here, they use the co-training to as a semi-super learning method. And here it's the same. Now, if you look at the causal data set, you can see very often times they are similar, right? Similar. And sometimes there's random error, right? So it could be better or worse, but basically they're similar. In that case, this is the causal data set, x causes y. Right here, you can see this is the anti-causal compounded case. Semi-super learning, which can make use of the additional unlabeled data, is always clearly better, right? So this means before you actually apply the method, you can even foresee the result regarding whether you can really make use of the unlabeled data to improve the prediction performance, right? Okay, so this is about semi-expert learning. Is there any question here? Maybe because I cannot finish this part before the break, maybe we should take a break right now.
Sure.
And then again, next part will be slightly longer.
Okay.
The last part of the last lecture. Now let's see how we can view domain adaptation transfer learning in a kind of principled way. Why? Because as many of you already noticed, in principle, domain adaptation or transfer learning is also a yield problem, right? Without further assumptions, it's not possible to solve the problem. Most problems are yield, you have to formulate additional assumptions so that you can really have non-trivial solution with guarantees, right? Even for regression, you saw it's a kind of yield. You have to have conditions. Right here, this is the basic setting of the domain adaptation or transfer learning. Here, I don't really want to distinguish between domain adaptation and transfer learning. Some people use them in different ways. Basically, the underlying assumption is the same. Even domain generalization can be seen as a kind of adaptation problem. So I don't really distinguish between those tasks. Here, we have a lot of source domains, and then in the target domain, we don't have a value of y, right? So we want to make use of the source domain information to predict in the target domain. Why can we do so? We know the distribution can change. Clearly, if the distribution can change arbitrarily, you have no idea what to do, right? And similarly, even in regression, in supervised learning, like regression, if in the future the test data are so different from the training data, you have no idea about it, you have to make assumptions. At some level, you have some kind of invariance, right? Or it's unification, it's unified model at some level. So here, clearly you have to make use of some high-level invariance or high-level representation. For instance, if you assume that y actually generates x, then y generates x, we know causal influence or causal connection is ontological, it's there. When we say y causes x, there must be a process so that y influences x step by step, right? You can trust it. Of course, in different scenarios, because of different value of temperature and because of different location, you can have different quantitative parameters or models. But with this one, you actually have a bridge. You can jump from one to another. Then you can make prediction. That's the intuitive idea. The traditional way of doing transfer learning basically assume covariance shift. This is covariance shift. Right here, x can change across domain, but py does not change. And at the beginning, I explained why. In this case, actually, you can do adaptation. Did I explain it? I forgot it. Okay, then let me quickly explain why. Even if px changes, but py x does not change, you may want to do adaptation. Here, y x, right, is nonlinear function with noise. You want to predict y from x. You always want to predict y from x, right? Sometimes y causes x, sometimes x causes y. But in prediction, we just use y as a prediction target. So now you can see if you want to use a simple model to make prediction, clearly the best model you want to use is very sensitive to where you are. If px right here is here, the blue one, then the best fitting linear prediction model will be here. If it's here, then the model will be here. Clearly, the optimal prediction model is sensitive to the distribution of x, although in this case, the conditional distribution of y given x is actually the same across the two scenarios, right? You have to do adaptation. Why? Because you want to use a simple model to make prediction. You just want to approximate the conditional distribution in the region you care about, right? Clearly, you care about the result will be sensitive to where you are. Of course, if you have a lot of data and if you have a very flexible model for prediction, you don't care about that. You don't have to do adaptation because the conditional distribution is the same across scenarios. But if you allow py given x to change, in this case, you have no idea. You cannot solve the problem. If X causes Y, and if Y given X can change, you have no idea about Y. Because in the target domain, you don't have the Y information, right? Fortunately, in most cases, I'll come back to this slide. You saw this before. Let me just go to another slide. Oh, I didn't delete it. Yes. Fortunately, in practice, very often times, what you want to predict is actually the cause of what you see. The label is the cause of the handwritten digit you actually see, right? Or you actually wrote down. Disease is the cause of the symptoms, but you want to predict why. And then you have a lot of models where you want to predict Y from X. However, you have causal influence from Y to X, as you can see from here. And you may have a change in Y, distribution Y, say, if you travel across different countries, the prior distribution of Y, disease, can be very different. But the conditional distribution of symptoms given disease will be almost the same. This is fine. This is what we call target shift. You may have this case. So the prior distribution Y is kind of stable, but the conditional distribution of X given Y could be very sensitive to a lot of things. I gave one example here. So Y is a rain, right? Suppose you are in this particular city, right? And then PY right here and PY in another place would be the same. As time goes on, you can see you have a distribution. But the conditional distribution of X given Y, the conditional distribution for you to see wet ground given rain can be very different, right? So you have this model, and you can put them together. So this way, in the new domain, you only have X value, but you want to predict Y. You want to see whether it is possible for you to really recover the joint distribution information. Because if you have the joint distribution information, you can always make optimal prediction. Remember, prediction or optimal prediction is always determined by the distribution, because you want to minimize the risk relative to the current distribution of the data, right? That's why it's sensitive to the distribution. Okay, good. Now, in many cases, Y causes X. Then in the previous slide, you already saw that if Y causes X, actually we have additional information. The prediction problem is much easier in non-stationary environment because, as explained before, because in any case, the effect X, the features, the symptoms, already contain the information of the cause, together with the information of the environment, where the light is from, and so on. And you can make use of your experience or the source domain information to learn the constraints, right here. And then by making use of constraints, you can just separate the information of the cause from the rest, meaning that you can easily predict the cause from effect in this case, even if everything can change, right? So to summarize, right here, if everything can change in a non-stationary environment, then predicting cause from effects would be very, very simple, but predicting effect from a cause would be very hard and almost impossible in some cases. Good, then what can we transfer? Right here, you can see a summary of previous work. So we know in many cases, we have invariant causal mechanism, right? Like the mechanism from disease to symptoms is kind of invariant. You can make use of such a thing for transfer learning. You can use invariant or transferable causal mechanism. You allow changes, but the changes follow some properties. You have a invariant mechanism right here. You have non-parametric transfer learning. Essentially, you want to discover, still, even if everything is non-parametric, you want to discover some low-dimensional kind of property of the changes, and then you can still do transfer. The idea is to detect, model, and utilize the changes. And okay, so I will skip this part. Now, it's good, but you want to make it more flexible. Yes. So in those cases, right, in the target domain, even if we have only the distribution of the target of the features X, since X is the effect of Y, we can predict Y. We can actually reconstruct the joint distribution. Just remember the shadow figure shadow thing. If you see X here, you can predict Y, right? You can even construct the joint distribution. That's Y. However, in practice, maybe you want to make it in an automated way. You want to discover and leverage the changeability of the distribution in complex scenarios. Specifically, if you have multiple domains, you can learn such a thing. You can figure out how everything can change, and then you can just make use of the property of the changes to make adaptive prediction, right? Now, let's see, suppose the change only happen to the relations among the measured variables, as you can see from this work. We can immediately solve the problem. This work is nice because with this view, domain adaptation is not a new problem. It's a standard problem. I want to have a graphical representation to explain how the joint distribution can change. And then after that, domain adaptation is nothing but the problem, classical problem of inference in the graphical model to see the posterior distribution of Y given the features in the target domain. It's nice because standard problem and it's optimal. This solution is optimal. You just want to find the posterior distribution. You make use of all the information that is available. You have a guarantee. Okay. So right here, previously I talked about causal discovery from non-stationary data. If you have multiple domains, you can apply the method and then you can find this graph right here. And in this case, for the purpose of domain adaptation, we say this is augmented graph because we introduce the theta variables. Basically, if the conditional distribution of say X2, given its parents, can change across domains, we introduce a theta variable into this guy to denote that, yes, this guy X2 also depends on some exogenous hidden variable, theta2. That's all. Now this is augmented graph. With this graph, you have an economic way to represent how the joint distribution can change. Remember, this kind of representation is the economic way to represent the joint distribution. Well, that's one way to look at the Bayesian network, right? You just want to find an efficient way to explain the distribution. Now you just try to go one step further. You introduce latent variable. You learn the structure from data with the causal discovery from non-stationary data, where you already infer the minimal changes. You want to find a simple representation. Still, you can figure out which part is invariant, which part can change, and they change independently because those variables are not connected. They change independently. And here, for instance, for X4, the distribution is fixed across domains. And for X7, it's the same thing. For X5, the distribution of X5 given parents is also fixed across domains because there are no theta variable into this guy. Given this graphical model, which you can learn from data, now in the target domain, you just want to make use of the new data. In the target domain, you have new values for the features, right? To infer the conditional distribution Y, given those things. You make the target domain specific prediction, right? You know, in graphical models, one problem is how to do inference in graphical models. There's a principled way to do so. Good, now you can make prediction. You can make sure it's adaptive. Yeah, okay. So according to Pearl, basically this is really the way to look at the domain adaptation problem because you have to figure out why things can change and how, right? However, you can still, right here, you can see, before I talk about another thing, let me explain some results and also make one thing clear. Here you can see the result. On the very right, you can see the result given by this method, basically called simulation result, and real world problems. You can see the performance is so much better. Why? You can see it, right? Why? Basically, this can be considered as a hierarchical way to make prediction. From data, multiple domain data, I can discover qualitatively how things can change. I have better understanding. My search space or my hypothesis space basically is reduced step by step in a reliable way. And finally, I have a very good understanding of the distribution. And then clearly, machine learning is about how you can leverage dependent and independent data and find a simple model to explain those things and then make prediction. This is a hierarchical way for you to really go to the simple model or go to the specific hypothesis step by step. As you can see from it, it's adaptive, right? It's also optimal. It's guaranteed to be optimal if you assume that the changes happen to the relations among the measured variables. This is a very strong assumption. Later, we'll just remove this assumption. The second thing I want to discover is that follow this one data set. We know causality helps. So far, I use causality to explain transfer learning. But is it necessary to say it's causality? We know that without further assumptions, we cannot make sure it's causal. We have to make assumptions in order to go from the statistical world to probability world and back to causal world. We have to make assumptions. But now I just care about the prediction. I don't really need to go to that world, right? So in fact, just look at this example. All of you remember this example, right? By Pavlov. So essentially, you can see the dog is very smart. The dog learns, right, how to really react to the environment. It's the association information. That we learn that it's association information, but the dog makes a very good prediction because this kind of association information is stable. You can just make use of it, although it's not causal. But you know this experiment, right? Okay, good. So without the strong assumption we cannot go to the causal world, then why bother? We don't have to go that far. In fact, in causal discovery from non-stationary data, we made some assumptions. For instance, there are no selection bias and so on. If those assumptions are violated, the discovered representation is still sufficient for the purpose of prediction, although it's not causal, as you can see from examples right here. Suppose this is the truth. Disease causes disease causes symptoms. Disease right here causes symptoms. And then you assign patients to different clinics or hospitals based on symptoms, because you cannot directly see the disease, right? You just assign them to different places based on the symptoms. And this is a very kind of a sensible process for you to see the different patients in across different clinics. Is that right? Is that right? Now you have data for XY across different clinics. If you apply the method of causal discovery from non-stationary data, what can you get? You are going to get this one, this graph. Might be surprising because here clearly disease causes symptoms. Sorry, I always wanted to say disease causes wet ground. I don't know why. The disease causes symptoms right here, and in the learned graph, it's reversed. Why? Can you see why? Do you trust me? That's correct. A lot of pressure, see? Okay, I will work hard to make sure I'm trustable. So, yeah. The problem is, first of all, you're totally right. Clearly, you try to see Y from X. The problem is whether across different clinics, your diagnosis, your diagnose system should be sensitive to where you are. Do you think you can use just the same diagnosis system across different clinics? In other words, do you believe PY given X is the same across different clinics? No. No. Are you sure?
Yeah, it's very easy because the standards in Europe and US are different. So they use different diagnostic thresholds.
Good. Now, basically, across Europe and the US, you are talking about the predicted value of Y. We are talking about true value of Y.
Well, yeah.
Then we have different predicted values, but we have.
Sometimes they argue about it.
Good. Now, suppose this is the case. You assign a patient to either Europe or US, for instance, right? And then do you think PY given X will be the same? when I ask the question this way, basically, it should be right. So now you can see the following thing. Right here in the first one, although you have a kind of this kind of link, right? You can see Y and S are independent given X. G separation. Right? The selection variable is independent from Y given X. Is that right? What does that mean? It means that PY, oh, for this part, I should use my iPad, otherwise I cannot see. So given the independence, it just said that PY given X and the different values of S would be the same. Right? For any value of S, I don't care. No matter where you are, which clinic you are, right? I don't care. Conditional distribution of Y given X will be the same because of conditional independent relationship. That means PY given X is invariant. Of course, PX will be different, right? Because you can see, given that, remember, we are working on the data generated from the conditional distribution, conditional S, right? If you conditional S, this guy, change variable will be dependent on X. So for X, clear distribution will change across different different clinics, but PY given X is the same. Is that good? So if you apply CD naught, you can even recover this guy, and you may say, oh, the conditional distribution to this given symptom is the same. That's true. It's not causal. Clearly not causal, right? But this is good enough for prediction. You can benefit from invariance in this case. Good. And this is one way to explain why, in many cases, actually covariance shift assumption. So we cannot say, in many cases, we cannot say X cause Y. Because basically in machine learning and other fields, we usually try to, it's an inverse problem. We try to recover the underlying hidden cause of what we see, right? This is not the case, but still covariance shift correction, right, for domain adaptation is very useful. Why? At least now you can see why. In many cases, we have different domains generated this way. Although Y equals X, we just assign data to different data sets based on what we see. As a consequence, the distribution of the features that we see can be very different, but the conditional distribution of Y given X is still the same. That's why. Although it's kind of very strange, it's not causal, but it's invariant. Okay, now let's try to distinguish between causal representation and compact representation. Without strong assumptions, relatively strong assumptions, we cannot say it's causal, but fortunately, in this part, we just want to do adaptive optimal prediction. That's good enough. I'll skip a second example, and then now let's, I have few minutes, I guess. I have 4 minutes. Let me remove this part, and then after that, my student, Yu will give a talk on fairness. He's a very good presenter, but he's not online, right?
I am actually online.
Okay. Good, good. So, well, where are we? I was talking about what? Yeah. I just said, if you believe changes happen to the causal relationships or dependent relationships among the measured variables, then the previous method is principled. It's nothing but the inference on graphical models, where the graphical model can be learned from data, right? However, in many cases, we cannot say so. As you saw from the previous work right here, we use that graphical model for domain adaptation right here. The distribution is different across domains. You just want to use a minimal number of changing components to explain the difference. And now the distribution is different, not because of the changes that can happen to the relations among the measured variables, but because of the latent variables, right? You can say they are compounded because clearly this guy will influence or generate a lot of measured dimensions. So now you know, oh, we can recover this guy. Each of those changing components without difficulty. We can also recover the invariant part without difficulty. Then you can see the correspondence across domains. You can do adaptive prediction. It's the same thing. Again, it's because we have a way to really represent how the joint distribution can change in an economic way. Then we can do adaptation. It's the same thing, although the graph we are using right here is different from previous one. The idea is the same. You have an economic way to represent how the joint distribution can change. And then you can do adaptive prediction. By the way, some people would like to use invariance to make prediction. That's good. I just want to rely on the invariant information. But very often times we can make use of chaining relations all the time, right? We can do so. For instance, if I go back to this graph model, should be next one. I have 2 minutes. Right here. I forgot what I wanted to show. Okay, in any case, I try to come up with something. So in this case, you can see, in any case, you have a way, modular way to represent how the joint distribution can change. Oh, now I see it. So in this case, you can see all the relations right here can change, but still you can find the right posterior distribution of y given x, right? You just make your decision based on posterior distribution, which can take into account all the available information. That's good. If you make use of invariance, you can see right here, it's so sad because only this part, say x7 given x3 is invariant. It's not really useful, right? So from Bayesian perspective, you don't have the binary decision regarding whether this is useful or not. Instead, you just discover all the information that is useful. You have the optimal way to make use of the information. That's it. It's not about the invariance. Even if everything can change in the world, you can still make optimal prediction by making use of the posterior distribution, given the evidence.
Since correlation includes correlations as well as causal relations, correlation-based prediction will be always better than causal predictions.
Oh, correct. So here I'm trying to say that you don't really care about whether it's a correlation or causation, as long as it's the base representation of how the joint distribution can change. It's good. As you can see from this example right here, this is you may say this is clearly not causal, right here.
Right.
This is not causal. It's just association, right? But it's good enough because it's invariant.
But
in this case.
my question is it good enough or it will be causal can never outperform correlation in prediction? Is it?
First of all, it's good enough. Second of all, you can go to the causal part. You can go to the causal if you have additional assumptions. You have to, you have to assume something.
Will that improve the result?
Oh, in this case, no. That's
Yeah.
why I said it's sufficient. You cannot, you don't have to go to the causal world because you are making prediction. Prediction is just about the kind of distribution. But if you want to do control, it's totally different.
Yeah.
As you can see from here, this is how you can, how you can implement it. I will forget about that part. Now let me just say this is how you can implement it, right? You want to find the invariant part, you want to find the changing part, and then by extending autoencoder, you can start to solve the problem. This is an alternative way to implement the idea. The previous one was to use the GAN, remember, right? We use GAN to model the distribution across domains, and then you have a joint view. This is similar. And now let me say a few words about how you can even look at reinforcement learning in the same way. in this work, basically it's a reinforcement learning environment. The environment can change. You can go from one scenario to another. You can go from the Earth to the Moon and so on. And then you have to figure out what part could change. As you can see from here, we can quickly identify whether there are changes to the mapping from the underlying meaningful state representation to what is observed, or maybe there's a change to the reward function, or maybe there's some change in the underlying dynamics for the state and so on. And then you can easily do adaptive reinforcement learning. In reinforcement learning, you really have to make sure it's causal, right? And in another work, we try to learn the meaningful hidden state representations. For instance, you may care about, in reinforcement learning, we care about not only the state that you can change. Sometimes you cannot change. For instance, we play a game together. I care about you, although I cannot change you, right? So we can just divide all those essential state representation into 3 parts, 3 subspecies, and they play very different roles, but you have to care about all of them. Okay, so you can do economic and adaptive reinforcement learning. And why are you here again? I don't know why. Sorry, there's something wrong. Okay, good. So I stop here. And the next part, you will see how to understand fairness and how to relate fairness to causality. Zhi, whenever you're ready, please. This
Thank you so much.
He has been working on fairness, and just recently he published an excellent survey paper in the space of fairness. So Zhi, please.
Thank you so much. So it's my great honor and very happy to be here. Thank you so much for the invitation. So the title of my presentation today would be what is and how to for ML fairness. And I would like to use 30 minutes time roughly to present a principal connection between causality and responsible AI, which is really a hot topic right now in the specific area of algorithmic fairness.
Cool. So could you please share a screen? Otherwise, I don't know how.
Sure.
To...
Is the slides showing up?
Yes, perfect. I'll ask him to.
Sounds good. Cool. So the outline of my presentation would be 4 parts. The first, I will introduce 2 motivating examples to give a taste of what exactly is algorithmic fairness researching about. And second, I will present a non-exhaustive list of currently proposed fairness definitions. And we will zoom into one of the causal fairness notions that have been canonical and very well researched in this area. And then we will present a flowchart consisting of 3 fairness spectra, which is taken from the survey paper Kuhn has kindly mentioned. I would like to use this flowchart to demonstrate how we think what is currently missing or less explored in the algorithm fairness literature. And then I will conclude with Q&A sessions, if there is one. So the very first motivating example would come from the Compass. So the Compass is the name of the software developed by a company previously called North Point. So this company no longer exists simply because there are too many lawsuits connecting to this single software they have been developed. So the initial goal of developing this software from the company point of view is to provide a helper tool for judges to help see what is the risk of recidivism of any defendant, and then to help the judge to decide the amount of bail and also whether or not to approve the pre-trial release. So the recidivism basically means whether or not this defendant will offend again during the time he or she is waiting for the trial. And here I show 2 charts and the table taken from the ProPublica report coming out in 2016. On the left-hand side, this chart is showing, first of all, the x-axis is the risk score. The higher the risk, the higher the possibility the software thinks the specific defendant will recidivist. And on the left-hand side, we can see that it's this, the y-axis is a count of the defendant, and the x-axis is a corresponding risk score they have been assigned by software. For African-American defendants, this distribution is relatively flat. For white defendants on the right-hand side, we can see that the software seems to skew towards the lower risk end of it, which basically means on a very high level, the software seems to think there is less risk overall for white defendants, but it's higher risk overall for African-American defendants. This can be more clear when we look at the table beneath two figures. The very first row, for example, we can see that for white defendants, the proportion of those who were labeled by software as higher risk, but actually do not reoffend during the pretrial waiting time is about 20%, but this number almost doubled for African-American defendants. So from this, we can see that there is a very intuitive idea of inequality, or something is not balanced, or there's a mismatch between the African-American defendants estimation versus the white defendant estimation. We will make those, try to make those intuition about bias or discrimination later on when I introduce the previously proposed fairness notions. The second example would be a loan application example. Say, for example, I'm looking for credit. I go to the bank and try to apply for a loan, for example. Then in the simplified pipeline, what the bank would do is to input my demographic information, for example, my name, my race, my sex, my age, and also my previous education or something like that. And then the model called FICO model, there are currently three main supplier of FICO score in the United States, which are Experian, Equifax, and also TransUnion. Then the bank will pick a FICO score of my FICO score, and then based on their pre-specified threshold, they will decide whether or not to approve my loan application. So in these two figures, these are figures taken from a 2016 publication about an equalized opportunity notion of fairness. We can focus on the right panel. The x-axis is the FICO score. FICO score is a number ranging from 300 to 850. So the higher the score, the overall lower the risk of default loan or something like that. So basically, the FICO score is an indicator from the software point of view, is an indicator of the applicant, his or her willingness or ability to repay the debt. So if we focus on the 600 over here, 600 FICO score over here, for Asian people, which is denoted by the solid blue line, roughly 20% of Asian people in that data set, or at least from the 2003 TransUnion FICO score data set, almost slightly more than 20% Asian people whose FICO score will fall below 600. But this number is much higher for African-American people, denoted by this blue, lighter blue dotted line, which means for a client, if he or she is from African-American community, then he or she will get a much higher risk of being denied, or probability of being denied by the financial institution if the financial institution decides to look at this TransUnion score at 2003. So from these two examples, we have seen that across the different scenario, we are comparing the result. We are directly related to certain specific attributes. In these two examples, these attributes are race. However, this a list of this protected, we call protected feature, is not only limited to race, and they are protected for different reasons. Say, for example, race and color, and also second gender are protected by law, and also other attributes are protected either by law or moral standards. The reason that we list those as protected feature is we do not want to use those features like whatever we want. We want to have some rule, or say a constraint when we utilize this kind of information. We need to be careful so that we are not violating the requirement by law, by moral standard, or a very intuition about the violate of justice or violate of fairness. And I should mention that these features are listed as protected feature is not to say that we cannot use them at all. So using them in a careful way is a much more effective and efficient way to protect instead of don't use them at all. Actually, one of the initial proposal in the algorithm foundness literature is called foundness without awareness, basically just to tease out those protected feature from the prediction. And there are critiques about that initial approach, simply because teasing out is a double-edged sword. Without using this, we cannot actually effectively counteract certain kind of discrimination or bias. So beyond previous intuition about the violation of foundness or the existence of discrimination, in algorithm foundness literature, the effort starts from trying to mathematically characterize the notion of discrimination or bias. And here in this this slide and also the following slides, this is a non-exhaustive list. So by 2020, there have already been more than 80 foundness notions that have been presented, and this number, I think, is more than 300 right now. So we cannot go through every single one of them because these notions sometimes are very specifically designed for a specific practical scenario. That being said, it's still worthwhile to look at different categories of foundness notions and to try to see what are the intuition behind those proposals. So in this page, I'm presenting this distinction between group level and individual level foundness notions. This is very obvious that when we define foundness or when we try to quantify discrimination, if we only look at group level, say, for example, Asian versus African-American versus white, as compared to we are looking at individual state of affairs, say, for example, we are focusing on Alice and Bob and try to see if they are treated in a relatively equal way. Then we have a definition on group level and individual level. So in the previous page, group level and individual level are relatively defined, focusing on the observational statistics without introducing any causal intuition or causal insights. Therefore, when we would like to have a more principled way, or when we would like to put more emphasis on the data strengthening process itself, previous literature has been considered the possibility of try to define discrimination or bias based on the estimation or provide some bounds on specific kind of causal effects. So the canonical, let's say the very first in the algorithm foundness literature at least, is called counterfactual foundness, proposed in 2017. And the following several ones are more or less more like variation or more refinement of the basic idea behind counterfactual foundness. Therefore, let's take a look at how they define counterfactual foundness and what are exactly counterfactual considered in this specific notion. So in this cartoon, I'm showing several circles. So for a circle that is being filled with color, this is trying to denote the positive decision. For example, if this is a loan application scenario, I am approved the loan. This is a positive decision. If I were denied the loan, this is a negative decision. And we can see that there are two groups of people, green people and orange people. And the third thing we notice is that there's a red box circle around as a contour over a certain circle. This is trying to denote that we are focusing on this specific individual. And on the left-hand side, this is on the green people group, and on the right-hand side, it's in the orange people group. So the basic intuition of the counterfactual foundness is trying to say that, okay, I would like to make prediction, and I would like to evaluate this on the individual level. So this is an individual level foundness notion. And the quantification they try to evaluate is consider two worlds. The first is the actual world we reside in, and the second is the counterfactual world where certain individual belonged to a different group. Say, for example, for this individual circled in red box, in the actual world, he or she is a green person. In the counterfactual world, he or she would be an orange person. But beyond that, everything should be the data joining process should be exactly the same. It's only that this person belonged to a different group in the counterfactual world. Then how can we characterize that? In the right-hand side, upper right corner, I have put a example causal graph right over here. Let's say we are considering A, the protected feature, to be sex, male or female, and the B would be the height of this specific person, and C would be this is a basketball player example. The C would be the position played by this specific player, and the Y in data set would be the score get by this player, and the Y hat is that we are trying to predict this. So if we were to use counterfactual foundness notion to apply this notion in this scenario, then we'll take every single individual player and try to see what would happen if he or she had been in a different sex, say male to a female or female to a male. And then we're making use of counterfactual analysis to derive, to infer about the I hat based on the causal model we have learned. If the Y hat is different, say, for example, the orange and green person actually receive a different predicted outcome, this is what they call a violation of counterfactual foundness. If for every single individual, these Y hat remain the same in the actual world and a counterfactual world, then this paper would say this scenario satisfies kind of requirement of counterfactual foundness. Notice that this is a very intuitive way of introducing causal analysis. And there are some follow-up works that try to refine this notion. Say, for example, in 2019, there are concurrent works that try to not only just going from the level of considering all paths from protected feature to the Y hat as a whole, they try to consider path-specific things. Say, for example, certain paths are problematic, while other paths may not be problematic. So they would like to consider the estimating or bounding of counterfactual causal effect along certain paths. And this line of work is called path-specific counterfactual foundness. And also depends on the kind of causal effects we're quantifying. It can be interventional causal effect or counterfactual causal effect. And then there are a line of works that trying to give, say, for example, path-specific interventional causal effect-based causal foundness notion. I know this is a little bit like a long name, but you can get the idea relatively easy, simply because they're trying to quantify a different type of causal effect. And also beyond the distinction between one category is defined foundness based on observational statistics without any reference to causal modeling, and the second category is trying to introduce causal effect when quantifying discrimination. Notice that when these notions are proposed, they are presented in an instantaneous way. So what I mean by that, we know that for setting, there are static setting versus dynamical setting. But this does not mean that we cannot apply instantaneous notions to dynamic settings. So by instantaneous notion, I mean the foundness is defined with respect to a static snapshot of reality. So a static setting obviously we can apply instantaneous notions. For every single individual step in a dynamical setting, we can also apply instantaneous notions. This is what I mean by the difference between instantaneous versus static and dynamic. There are research papers that have been considered the possibility of introducing instantaneous, the analysis of the delayed impact of applying my instantaneous foundness notion at time t equals 0 versus what it's going to be like at t equals 1, for example. And there are also recent works, for example, this one is our recent work in iClear 2023. We're trying to propose a foundness notion that is not only instantaneous in the sense that we would like to build in some dynamic flavor into the foundness notion itself, such that we view foundness not only as an evaluation on a snapshot, but also a goal we would like to achieve in the long run. So I think this distinction will become more obvious when we see the foundness flowchart in the later slides. And also, when we trying to define discrimination, previously we can choose to define based on the outcome. Basically, what is the difference between y and y hat? There can be additional consideration because the difference between y and y hat can have different meanings in different scenario. And sometimes these are closely related to the welfare or well-being of individuals. And therefore, in the previous literature, these are considered as more like going beyond the simple distinction, say, for example, accuracy or MSE, and trying to give some practical implication of the difference of y and y hat, which are listed as a welfare consideration over here. So in this chart, I'm presenting the previously mentioned foundness flow chart that can consist of different consideration in different foundness spectra. So this is overall, in this slide, I would like to give like an overall implication or what exactly is the flowchart is trying to talk about. We have, say, for example, at the very beginning, we have the data. And depends on what we're trying to evaluate. Are we evaluating the data itself? Are we evaluating the information utilization? Or are we trying to analyze the long-term impact of my implementation of current decision-making system? The founders consideration can have different emphasis. And as we see each single spectrum of the flowchart, we will see how causality will introduce unique insight and provide us with a very useful tool to achieve different goal in different foundness spectrum. So the very first spectrum is what we call foundness with respect to the data generating process. So it should be very intuitive because we are trying to analyze the data generating process itself. Then, without introducing causality, or we would like, how can we actually manage to quantify the discrimination in the data generating process itself? It's very natural to introduce causal analysis tool to help us to achieve our goal of quantifying what exactly is happening, what is wrong with the current data we have. There is a saying called, all data is biased, but some are useful. So this is a quote from a tutorial in 2022 in Europe's conference by Professor Isabel Gluon. So I think this is a very intuitive idea of correct data. We would like to correct the data at hand, but however, without introducing the causal analysis tool, how can we do this, right? And the second implication is that when we say a data is unbiased, we're actually implicitly putting some intuition or assumption on it, because different foundness notion might not be compatible with each other. And some foundness notion may put more emphasis on data itself versus the predicted outcome. So here I double quoted the clean to try to indicate that when we say a clean data, it does not mean that the data is not problematic from all perspective. It simply means that the current data satisfy certain notion of foundness with respect to data generating process. Another thing we should notice is that in this first spectrum, there's no specific or explicit introduction of prediction or decision making. So the reason is that when we quantify the data itself, we're simply be an auditor. This auditing process should not be relevant to what kind of prediction or downstream task we would like to apply. And this kind of focus on the prediction should be in another spectrum, which we call the foundness with respect to the predicted outcome. So different from the previous, we are not trying to look at the data generating process in the original data or say the underlying process. We are evaluating the predicted outcome. We are trying to quantify bias on the predicted outcome of the decision-making system or automated predictor or something like that. So here the input would be still a data, but we are actually implicitly assuming the data at hand is not problematic, in the sense that when we try to quantify the bias in predicted outcome, we're not being bothered by any problem in the data itself. I know this will sound actually weird, because if the data is not clean, how can we make progress based on the data, based on the biased data? But unfortunately, this is a kind of an implicit assumption in a lot of algorithm foundness literature. Because if we were to use a tool such as, for example, to evaluate the accuracy or evaluate MSE, we are implicitly assume that the baseline we're evaluating against, which basically the Y in the data, is not problematic. Otherwise, why are we getting closer to a biased data? So that is why we think in the predicted outcome, there is indeed this implicit assumption. And let's put this implicit assumption aside and then try to evaluate what exactly is going on in the predicted outcome. The reason is that even if the data is not problematic at all, if the information utilization is not careful enough, we can still introduce problematic aspects in the prediction. And again, this double quoted fair over here is trying to indicate that the prediction satisfy certain notion of foundness with respect to predict outcome. And the story does not end here, because in a more dynamic consideration or a long-term consideration of foundness, we're not done after completing one single step of fair prediction, producing a quoted fair prediction. Sometimes this prediction and the data will have an interplay. So by interplay, I mean the next step, the state of affairs in the t equal to 1, depends not only on what kind of data you're using, and also what kind of the prediction are made in t equal to 0. Sometimes the data generating process of the underlying process and the data generating process for the prediction will have some kind of like an interaction. And the future is not simply defined or fully determined by any one of them. So if there is such kind of interplay, when we're trying to evaluate the long-term impact of current decision, or are we getting better towards a fairer future, there is a consideration with respect to the induced impact of current implementation. And also another reason of consider this, singling out this kind of consideration to a specific spectrum is that sometimes the scope of consideration will go beyond any single prediction or decision-making policy. Say, for example, I would like to evaluate in 20 years how the career, or say the life plan of people in this community would be like. And this is not fully determined by any single decision-making process. Say, for example, evaluating a loan application or evaluate the school admission. These seemingly separated decision-making procedure will intertwine, and the future is decided by how they interplay or interact with each other. And that is why we think singling out this fairness with respect to induced impact can be a fruitful and a very good way of thinking about long-term fairness with great potential. And another reason, I think maybe slightly more important, is that we have a closed loop. So what I mean by that is, let's say we go through data, and then we evaluate whether data is good, get a clean data, and then we evaluate our prediction is making information in a relatively correct way and get a fair prediction. They will generate new data if possible. We can collect them and go through this pipeline again. So this closed loop will give us a more principled sense of, are we actually doing something good? Are we actually getting closer to what we intend to do to derive a fairer future? So the role of causality in this spectrum is also very significant, because without causal analysis or causal modeling of the interplay between different data generating process, we cannot give a relatively principled and also precise way of quantifying how this interaction will have a good or have a positive or negative impact on the future. So yeah, so Y3 spectrum, as we have seen before, we have different emphasis in different kind of fairness analysis. If we were to focus on data, then we should go with data generation process spectrum. If we also care about information utilization, then we're probably going to introduce predicted outcome spectrum. And if we try to go further and try to see, are we getting a fairer future? Are we actually going towards the direction we intend to go? We definitely need to introduce these induced impact spectrum. And these spectrum are not they are not introduced in an unnecessary way, in a sense that they do not contain each other as like a subset of the consideration. So for this pair, data generation process versus predicted outcome, this is relatively obvious because we're focusing on data versus y versus y hat. So for predicted outcome versus induced impact, this distinction is from the fact that we are not limited to considering every single prediction system or decision-making system. Sometimes this interplay will involve external forces or entities that go beyond the control of the algorithm, current automated decision-making algorithm. Say, for example, the school admission decision process made by the school committee do not have the control over what kind of policy or subsidies will be put in this, or kind of investment will put in this neighborhood. There are external entities. And for this pair, the data generation process versus induced impact, their relative emphasis is also very different. For induced impact, although we are trying to consider interplay, such interplay is not characterized by data generation process of underlying process alone. There is, for data generation process, then this external role or external player would be prediction systems. With different prediction system, we will have different kind of interplays. And those different kind of interplays with their different dynamic properties will let us know how the fairer future will look like, or are we actually going towards the right direction? So yeah, as we have seen before, although these three spectrums seem to have a different emphasis with respect to the objects of interest or what kind of a thing we can control, we cannot control, there is a thing shared, which is causality can provide insights in every single spectrum and help us to do the analysis in a principled way by either focusing on the data generation process itself or try to model and focus on the interplay between the prediction system and the data generation process. And with that, I will conclude my presentation. And these are the references in this presentation. Thank you so much.
Yeah. Any questions regarding this part? It's a kind of, I asked Zoe to give a very brief one. That's why you can see details are not included. Do you have any questions about the basic idea or about the connection between causal understanding and fairness? No question? Okay. Thank you very much. So you know why? Basically, we are supposed to end the lecture right now. That's why they are very thoughtful. I don't want to have others to wait. Okay. Thank you very much. It's wonderful. Thank you.
Thank you.
Okay. So let me just give a summary. Sorry. Okay. It's coming. In this class, I hope you really see that causality matters, right? Without the causality, without the causal thinking, you cannot really solve a lot of problems in a principled way. Sometimes you can do wrong things, right? Because you have to care about the consequences of different things. You have to find the right thing to do. Good. And then I hope you also learned about how to really discover causality from data. Essentially, you have to make assumptions, and very oftentimes, different kind of simplicity can really help in causal discovery. First of all, there are 3 types of independence they can really help you really discover causality from data. You can even think of simple independence as a kind of simplicity assumption, because you try to go from independence to lack of link, causal link in the world. So it's a simplicity assumption. If they are independent, I don't have link right there, right? If they are conditionally independent, I don't have edge in between. If they are independent noise and regarding noise and cause, then basically I can say that's really the noise. If I have the noise, I know this is the causal process, right? Because without really having a causal process, you cannot even say it's noise, right? Noise is nothing but omitted factors in the process. And furthermore, if you have non-stationary environments, you can have minimal change and independent change properties in the causal modules. Okay, all of them can be used. And furthermore, if you try to go further to infer latent variables, and you can further benefit from other kinds of simplicity. For instance, you saw two things. One is how to make use of rank deficiency condition, right? And the second thing, you saw three things. The second thing is the sparsity discussed by Yuja. You can see why, because with sparsity constraint, you can really show that the underlying picture is recoverable, and sparsity is clearly a simplicity assumption, right? And in some way, sparsity assumption is consistent with faithfulness assumption. Okay, you don't want to use a very complex model to explain the data, if it's possible. And furthermore, you saw the gene condition, generalized independent noise condition. That's nothing but a generalization of the independent noise condition, right? So all of them can be seen as different kinds of simplicity assumptions. Of course, you may question those assumptions. Fortunately, most of those assumptions are testable. Okay, that's good. And finally, you also saw that in a lot of machine learning and AI systems problems, you care about the causality, you care about the causal representation learning, especially if you try to do, say, reinforcement learning, you have to make sure it's causal, right? And if you want to do transfer learning, you may want to find some kind of compact representation of the changeability of the distribution. And very oftentimes, especially under some assumptions, this representation is the same as the causal representation. But without those assumptions, this representation is compact. You can still benefit from it if you try to do optimal prediction. Why? Because in all those cases, you have to go beyond the data. Then you can have a broader view, and you can see in this particular domain what you should do, right? And finally, you can see that under rather mild assumptions, you can really recover latent variables and even latent processes from data, and you can allow the latent variables to be causally related. This means we have a basically new way, automated way to really discover the underlying concepts, underlying variables, and underlying laws from data, right? That can hopefully increase human knowledge. This way we can make the human world bigger and bigger by analyzing what we have observed. And very importantly, generally speaking, with all those methods, you can show that the truth is identifiable. So that's so essential because you are talking about the causality. And finally, I would like to show my to thank those people, including my students and former students, Biwei, Mingming, Feng, Weiran, Peter, Yuja, Ignavia, Xinshui, Zeyu, Haoyue, Linjing, Xiangchen, Yemin. Okay, good. Thank you very much, guys. And I would like to thank my collaborators and friends, including Clark, Peter, Bernard, Apple, Richu, Gigi, Jill, Yoda, Richard. And of course, special thanks go to our organizers, Yang. Thank you very much. We were together with Grace, Fanny, and Rojas. You did a great job. So we really enjoyed the last 5 days. Thank you so much. Of course, thank you very much for making this course so nice, right? Your feedback is so nice, and the discussion is very, very inspiring. So I hope you really learn something from here, and I hope you can go very quickly in a very good way in the very near future in the causality research domain. Thank you very much.
Yeah, I just take a minute or two to say a few final remarks. Well, first I echo what Ben just said. Really appreciate the help from our amazing staff members including Judy's, who is I think outside the door, who basically handles everything from booking this room for the as a conference venue, design the tag, and basically put things together. But also we have two other staff members you probably haven't seen, Carrie and Kim. They are in charge of, for example, travel award reimbursement. Some of you, if you're awardee, you probably already got in touch with her. Also Kim, who is in charge of the registration. I also like to thank Bonnie and Raj. They are, also serve on the organizing committee. So they have been really helpful from the very beginning, preparing a proposal to NSF to, fund this conference. So I really like to thank them again. Of course, we really like our main lecturer, who actually, give us 10 amazing lectures on, from fundamental causal graphic model structure learning to the most recent advancement of causality research. So obviously, without you, the conference would not be possible. And I also like to acknowledge my funding agents at NSF, the National Science Foundation's financially support this conference, as well as the Institute of Applied Math and Computational Sciences at Texas A&M, who also provides some funds to make this conference possible. And also, I'd like to thank the Department of Statistics here at Texas A&M, who of course provide amazing staff support for this conference. And of course, just as Quinn said, thank everyone for coming to College Station for this conference, and especially if you sort of stick with us towards the very end of this 10 amazing lectures. Thank you very much. With that, I'd like to conclude the conference, and hope you all have a very productive summer. Thank you very much. I guess we can still have a few, 10 minutes for discussions, but I guess you have to leave around 4:15, right? Okay, if that's okay with you.
Feel free to leave.
Yeah, feel free to leave. We can have discussion here if you want to stay for maybe the next 10 or 15 minutes. Oh, if you can do me a favor on your way out, if you see Judy's, we really appreciate if you can say thank you in person to her. Thank you very much.